When I told my coworkers I was doing a video on the history of anthrax, they were concerned. And I understand why. When most Americans hear anthrax, they either think about the band or they think about envelopes full of white powder back in 2001 and think about its role as a bioweapon. But anthrax the disease has a different impact on the history of medicine. Bacillus anthracis, the bacterium that causes anthrax, was the first microbe ever identified as the cause of a specific disease. Scientists had looked into this relationship between germs and diseases for centuries, but research by German scientist Robert Koch provided killer evidence for the theory. It's not a stretch to say that anthrax fundamentally changed how scientists researched infectious diseases. So in today's video, we'll get some background on the history of anthrax disease, look at why it made such a good candidate to kickstart germ theory, and how treatments and prevention efforts have changed over time. But first, let's get some background on the biology of the disease itself. Bacillus anthracis, the germ that causes anthrax, is a rod-shaped bacterium with an interesting survival strategy. It has the ability to form a spore, and these spores are super resilient. They can stay dormant but viable for decades outside of a host. We'll get into the routes of infection in a minute, but when the spores enter the body, they're engulfed by macrophages, which are big immune cells. From there, the spore shifts into its bacterial form and starts replicating. And even in the bacterial form, Bacillus anthracis is resilient. It's surrounded by a little capsule that makes it really tricky for our immune systems to kill. But they do their damage thanks to a combination of three factors: protective antigen, lethal factor, and edema factor. Here's how it works. Protective antigen lands on healthy cell surfaces and provides an attachment point for the other two factors. Then, after the cell engulfs this little antigen package in a bubble called an endosome, that protective antigen acts like a pore that allows the other two factors into the cytoplasm of the cell. They go on to become two toxins: lethal toxin and edema toxin. Edema toxin messes with some of the cellular messaging systems within the cell, resulting in edema, or swelling. It also keeps those macrophages from working properly, which lets the bacillus evade the immune system further. Then lethal factor triggers the host cell to self-destruct via apoptosis. Then when it's time for the host to die, the bacteria create swelling around the lungs, then sepsis and shock that leads to death. When the host does die, the bacteria turn into spores again, which might infect another host in the future. Now, I know that I always thought of anthrax as something you inhaled, but there are actually 4 routes of infection, and each one works a little differently. Around 95% of cases of human anthrax happen through the cutaneous route. This is when the bacteria or spore get in through a break in the skin. Luckily, it's treatable with antibiotics if it's caught early, but if untreated, it can be fatal around 20% of the time. In this version, the bacteria replicate and produce their toxins locally. This presents as a cluster of fluid-filled blisters, which eventually pops, leaving behind a gnarly-looking necrotic lesion called an eschar. It ain't pretty. Also, you can open your eyes again. This is where anthrax gets some of its historical names, like the Greek anthracis, the Latin carbunculus, and the French charbon, all meaning coal. They're named after the eschar, which looks like a lump of coal. Meanwhile, the German translation, Milzbrand, translates to spleen fire, which is an awesome name. Less common but more deadly is the gastrointestinal route. This is when you eat something contaminated with anthrax bacillus, like raw or undercooked meat. Then through some kind of break in your GI tract, it spreads to the lymph nodes or bloodstream. If untreated, this route can be fatal in more than half of cases. This is how most livestock get anthrax. A cow or sheep comes along, eats some grass, and ingests some anthrax spores. Next, there's the inhalation route, the kind from the 2001 attacks. The infection starts when the victim breathes in the anthrax spores. They travel to the lymph nodes around the lungs, and from there, the bacteria emit their toxins and the victim can die within a few days. It's not that inhaled anthrax is like an extra virulent pathogen, it just gets into your bloodstream more quickly than the other forms. Now, it's really uncommon in humans, but it is the most deadly, and the hardest to treat, even with antibiotics. It was around 45% lethal during the 2001 attacks, but historically killed anywhere from 80 to 100% of its victims. Finally, there have been some reports about injectional anthrax in Northern Europe, but they're really rare, and we don't have a ton of data about it yet. Alright, now that we've got that little primer, we can finally get into the story. Humans have been documenting what was probably anthrax for thousands of years. After all, anything that affects your livestock is going to be pretty important to keep track of for most of human history. Like, some scholars think that one of the 10 plagues in the Old Testament is a reference to anthrax, since it was a livestock disease. Others say that anthrax is referenced in Homer's Iliad, and Arabic scholars described a similar cattle disease in the 12th and 13th centuries. It also showed up in local histories, since anthrax tends to linger. It would infect some cattle, they'd die, and the microbe would become a spore and hang out in the grass until it was eaten again. This phenomenon was common enough that farmers had to remember where anthrax-infected livestock were buried so that they could keep their existing cows from grazing on infected grass. By the Middle Ages, global trade of livestock and animal products like leather and wool spread the disease internationally. As a result, people documented anthrax epidemics more often. In 1613, there was a full-fledged anthrax pandemic in Europe, which killed around 60,000 humans and a bunch more pets and livestock. That was followed up in 1709, when outbreaks of cattle diseases like anthrax, rinderpest, and foot and mouth disease wiped out livestock populations. Another epidemic in Haiti in the 1770s killed over 15,000 people, and this one was probably intestinal anthrax spread through beef consumption. Unfortunately, this is also where historical documentation gets tricky, because anthrax might have also been a non-specific catch-all for multiple diseases. So a reference that we think is anthrax might actually be smallpox or plague. But in general, anytime someone described visible skin lesions, swollen lymph nodes, bleeding from the nose or mouth, and deaths associated with animals, historians tend to lean towards anthrax. But back then, it was really hard to tell one disease from another. Nobody really knew how anthrax spread, and the idea that microscopic life could cause disease was still a niche theory. And what's worse, we're coming up on a time throughout the 18th and 19th century when anthrax started to become an occupational hazard. See, by the 1700s, the mass production of textiles, especially wool, was becoming a big part of industrialized economies. And in the 1800s, doctors were noticing cases of an anthrax-like disease popping up in folks who worked with animal hair. Eventually, this disease earned the name wool sorter's disease. And this is where a French doctor named Nicolas Fournier comes into the picture. Alright, so you know how everyone's first job is kind of awful? Well, when Fournier was just 20 years old, he was recruited to help treat a bubonic plague outbreak in Marseille that killed 80,000 people. Obviously, not a fun way to kick off a career, but that gave him experience assessing marks on the skin in an epidemic setting. And when he got back to his hometown of Dijon, he was greeted with the same thing, except this time it was an outbreak of charbon, or anthrax. This dude could not catch a break. Fournier noticed that humans who got anthrax tended to work around animal hair. Not all of them, but enough for him to notice a pattern. And those classic black eschars were the first clue. After a little practice, he learned how to tell them apart from other skin lesions. So when it came time to publish his findings in 1769, Fournier did something clever. Instead of classifying the disease based on symptoms, he classified anthrax infections based on how they were acquired. According to Fournier, there were two types: spontaneous and contagious anthrax. Spontaneous anthrax was an old-school miasmatic model disease, caused by working outside in the hot sun all day or breathing in vapors from decaying carcasses in the ground. Meanwhile, the contagious version was written more like how we understand anthrax today. Fournier described the cutaneous version with the black lesions, and an internal version that someone might contract after eating contaminated meat. And all of this gave scientists a more consistent idea of what anthrax looked like clinically, both in humans and animals. But the next big question was what caused it. And around 1849-1850, the team of Casimir Davaine and Pierre Rayer found it. They took samples of blood from sheep infected with anthrax and saw these little stringy, wiggly bacteria in them. They had finally found bacillus anthracis. Each bacillus is pretty big as far as bacteria get, anywhere from 1/2 to 3 micrometers wide and 2 to 9 micrometers long. But they can also form these long strings of bacteria. So even with 19th century microscopes and without gram staining, scientists could still see them. Over the course of the 1860s, Davaine repeated some of those transmission experiments in animals. He'd give blood from one animal to another, and he'd notice that only blood from an infected animal could transmit anthrax. Blood from a healthy animal could not cause anthrax. And he kept finding the same stringy bacillus anthracis in human anthrax sores, which meant that both the animal version and the human version of the disease shared the bacteria in common. And over the next few years, more scientists noticed the same thing. They could find bacillus anthracis in anthrax victims, but couldn't find it in healthy animals, or in animals that had died from other diseases. Davaine also concluded that this bacteria was unique to anthrax disease. It was different from the bacteria in putrefied foods like rotten meat. Alright, a bit of a breather here. When I was researching for this video, it seemed like Davaine got really close to connecting the dots and saying that bacillus anthracis caused anthrax. Like, from the experiments that he and his predecessors had done, it seemed like an obvious cause and effect relationship, but scientists back then had reason to doubt. See, by the mid-19th century, scientists knew that some diseases were contagious, but they couldn't show why yet. right? They'd inoculated animals with anthrax-infected blood, but that had all kinds of stuff in it. To show that a germ caused disease back then, you'd have to isolate just the microbe and watch it cause a disease all by itself. This is where Robert Koch comes in. Koch got his medical training at the University of Göttingen, where he studied under a bunch of famous scientists. One of those scientists was Jacob Henle, who anatomy students know for the loops of Henle in the kidneys. Henle was a big proponent of early germ theory, what he called contagium animatum. Unfortunately, he was never able to come up with rock-solid evidence to support his theory, but he did outline a set of criteria for saying that a specific germ might cause a specific disease. These criteria became known as Henle's postulates, and they influenced Koch's work big time. So our sweet young Robert started practicing medicine in Wolstein, what's now part of Poland, and within 4 years they had documented over 500 deaths from human anthrax and around 56,000 anthrax deaths in livestock. That's a legit public health problem, so Koch decided to investigate. He started by taking a bunch of healthy mice and injecting them with blood from animals either infected with anthrax or from healthy animals, really similar to what Davaine did before him. All of the mice that received blood from an animal infected with anthrax died, some within 24 hours, meanwhile the other mice survived. Got it. Something about the blood is infectious. But what? Well, when he looked at the mice's tissues under a microscope, he found the same stringy microbe that his predecessors did. But maybe it was just there by coincidence. Maybe it was correlation, not causation. So Koch took samples of infected blood from one mouse and inoculated it into a healthy mouse who went on to develop anthrax. He repeated these inoculations and kept finding bacillus anthracis in the blood, which gave him the idea that this thing was a living, self-replicating microbe. But the logistics of testing whether bacillus anthracis by itself caused anthrax was going to be a challenge, because Koch had a hard time getting the inoculations to cause disease if he took them a few days after the original animal died. And that was confusing, because anthrax had this reputation for hanging out in fields for decades after an outbreak. Something didn't line up. Koch needed to figure out a way to make copies of the bacillus in a more controlled setting, what's called culturing bacteria. From there, he could isolate them and either throw them under the microscope or inoculate them into an animal. So he took some of the bacillus and injected it into a rabbit's eye. After a while, the transparent liquid in the eyeball, the aqueous humor, turned all cloudy as the bacteria replicated. Now here's why I find this story so interesting. Koch's team would go on to develop tools like agar and the Petri dish, tools which are fundamental to microbiome labs today. But at this point, Koch was working in a rural setting without the greatest tools. One of my references said that he mostly used a microscope that his wife got for him, which I find so charming. Even more so because his next big challenge depended on looking at these microbes under the microscope. He took some tissue from an anthrax-infected spleen, put it on a slide, threw in some eyeball fluid, and repeated the process under different temperatures and humidities. He noticed that those classic stringy bacilli would show up when the little environment on the slide was warm and wet. But after a while, he'd watch the bacilli form these little spheres, and the rod-shaped bacilli started to disappear. At this point, the eyeball fluid would be dried out, so he would reapply the fluid, and that would cause the bacteria to creep out of the spheres again. He hypothesized that these little spheres were spores, and they would let the bacteria live outside of a host for a long time. And obviously, that still doesn't prove cause and effect, but it was the missing piece of the puzzle. He'd figured out how to culture the anthrax bacillus, and figured out its life cycle and when it might be infectious. Now it was time for the big one. He cultured a fresh batch of pure bacillus anthracis, picked out some bacteria, and inoculated them into healthy mice. This wasn't blood, it wasn't whole tissue, this was pure, isolated bacilli. The animals inoculated with pure bacteria died, and Koch became pretty sure that he'd found the cause of anthrax. So, he wrote up all of his observations from the past few years, how he cultured the bacteria, the life cycle of the spore, and the cause and effect nature of the bacillus, and published it in a botany journal in 1876. I'll link the primary source down in the description. Check it out if you can read German. The next year, he published another paper on anthrax, but this time he included these, the very first published photographs of any bacterium in a scientific journal. Over the next few decades, he'd tweak this cause and effect relationship between microbes and disease into a set of guidelines that help scientists determine which germ caused which disease. These points became known as Koch's postulates. This is why I don't think it's a stretch to say that anthrax is one of the most important diseases in history. The protocol for showing bacillus anthracis was the cause of anthrax would help scientists find germs that caused other diseases in the future. Koch went on to have an incredible career in science, including finding the germs that caused tuberculosis and cholera, but his research on anthrax earned him a ton of immediate attention in the scientific community. And one of those interested scientists was Louis Pasteur. See, Pasteur's lab created a vaccine for chicken cholera the same year that Koch published his first anthrax paper. And the novel thing about this particular vaccine was that it was purposely an attenuated vaccine. By exposing the germ to air, they'd weakened the cholera bacterium to the point where it didn't cause disease anymore, but still taught the immune system how to recognize and destroy the full-flavor, non-attenuated bacteria. So Pasteur thought that he and his lab could use the same technique they'd used on the chicken cholera bacteria to create a vaccine for anthrax. But bacillus anthracis was a different beast. Since the bacillus forms a spore when exposed to air, it didn't matter how many times the Pasteur lab cultured it, they couldn't create a weaker version. I mean, the bacillus can live dormant underground for decades, maybe centuries, so it's no surprise that repeated exposure to air alone didn't reduce virulence. Meanwhile, elsewhere in France, a veterinarian named Jean-Joseph Henri Toussaint created an anthrax vaccine using chemicals to attenuate the bacteria, not air. And by 1880, an English scientist named William Greenfield had successfully vaccinated livestock against anthrax. Now, by all accounts, Pasteur was a big-time showman, and he must have been feeling the pressure to keep up. So he and his team decided to bring the heat. Literally, they started trying to attenuate with heat and air. When they warmed the bacteria to 45 Celsius, they stopped replicating, and that was no good. They wanted an attenuated but live bacillus. Luckily, after a few more trials, they found their Goldilocks temperature between 42 and 43 Celsius. Just right for keeping the culture alive and replicating, but less virulent. And in 1881, Pasteur went public with it. And man, did this guy love a spectacle. He decided he'd demo the effectiveness of the vaccine at a village outside of Paris called Pouilly-le-Fort. It would be outside in the open with newspapers and media attention everywhere. He got some sheep, some cows, and goats together and sorted them into two groups, one that would get vaccinated and an unvaccinated group. On May 5th, 1881, Pasteur and his assistants injected 24 of the sheep, 6 cows, and 1 goat with their first dose of the anthrax vaccine. Then they waited 12 days and gave them their second dose. Meanwhile, the unvaccinated animals, which were 24 sheep, 4 cows, and another goat, must have been looking at them thinking, that looks like it hurts. Glad it's not me. Well, maybe not. Because on May 31st, both groups were injected with a virulent strain of isolated bacillus anthracis. 48 hours later, the scientists checked in on the animals, and all of the vaccinated ones were perfectly healthy, while the other group didn't fare as well. From the English translation of his 1881 paper, quote, in contrast, 21 sheep and the goat which had not been vaccinated had already died of anthrax. 2 other unvaccinated sheep died in front of the viewers, and 1 remaining sheep died at the end of the day. It honestly sounds like a sitcom. Like, I don't know, Louis, how can we be sure it was the vaccine that protected them? And then those 2 other sheep keel over for a macabre comedic effect. Now, the unvaccinated cows didn't die, but they did develop some weird swollen spots, which the vaccinated cows didn't. So it wasn't as dramatic, but it did still point towards effectiveness. But of course, the drama is what made this experiment so famous. Remember that Toussaint and Greenfield already tested vaccines for anthrax before Pasteur did. And asterisks here, pause if you want to read my disclaimer, Pasteur's notebooks say that they used Toussaint's attenuation method before they figured out the heat thing. Either way, Pasteur's experiment got all the media coverage at the time, so that's the story that became most famous. So after the big public experiment, the newly formed Pasteur Institute scaled up their vaccine production, and farmers were able to protect their livestock against a serious disease. And while that's great for reducing anthrax, we could still use some human treatments. The next part of the story starts in Bradford, England in 1878, where a local newspaper gives the following quote, within a month, 3 wool sorters have died from blood poisoning contracted in the same shed of the same factory in Manchester Road. Occasional deaths from blood poisoning, through the handling of some foreign wools, may perhaps be inevitable, but the recurrence within so short a time of 3 such cases seems to suggest that either the wool itself or the shed in which it was sorted is specially unwholesome. This was just one of the mills seeing more cases of the old wool sorters disease in the late 1800s. So an epidemiologist named John Henry Bell decided to investigate. One day, he made a house call for a mill worker who was dying from wool sorters disease, took a blood sample, injected it into lab animals, and they died a few days later. Bell had read the recently published paper linking bacillus anthracis to anthrax, so when he looked at the infected animal's blood under the microscope and found a bunch of the bacilli, he concluded that the disease was indeed a type of anthrax, but a pulmonary version. The spores must have hung out in the wool and animal hair, and the wool sorters inhaled them. Assuming that anthrax was an occupational hazard for these mill workers, he put pressure on wool manufacturers to improve safety standards. Stuff like disinfecting the wool with steam and antiseptics before anyone handled it. The manufacturers said, yeah, that's a lot of work, no thank you. So in 1880, when Bell attended another death from wool sorter's disease, he wrote on the death certificate that the man died because his negligent employer didn't disinfect their wool. Then he went to the police and insisted that they kick this up the chain of command and pass legislation to prevent this kind of thing from happening in the future. By 1884, some of Bell's recommendations found their way into voluntary guidelines that manufacturers could adopt. But by 1899, the British Home Office formalized these practices as policy. It was one of the first times that a disease had been recognized as an occupational hazard. Some of the more updated policies involved vaccinating as many animals as possible, decontaminating domestically made animal hair products, and making sure that any imported animal products were anthrax-free. By the turn of the century, there was at least a decent anthrax vaccine for animals, but scientists were still a few years away from a human vaccine and antibiotics. And in the meantime, some of the treatments for humans were brutal. I found stories about doctors cutting out or cauterizing the eschars. But then in the 1930s, a scientist named Max Stern found a strain of bacillus anthracis that was just a little bit off. This variant of the bacterium didn't have one of its virulence factors, and had lost its ability to form the protective capsule around itself. And when he inoculated animals with this strain, he was able to induce a protective immune response against more virulent forms of anthrax. It's not safe enough for humans, but it went on to become the most common anthrax vaccine for livestock. And better animal vaccines reduce the number of human cases. To this day, one of the most effective ways of reducing the incidence of anthrax in humans is to control anthrax in the animals we interact with. We saw the same thing in the rabies video. Countries without rabid dogs rarely have cases of human rabies. By the 1940s, there were good strategies for controlling animal anthrax, but we're also coming up on the golden age of antibiotics. And when penicillin and other beta-lactam antibiotics start coming out in the early to mid-40s, they prove to be very effective against the gram-positive bacillus anthracis. Even these days, anthrax is sometimes treated by good old penicillin or amoxicillin, although there are strains of the bacillus that make penicillinase, which is an enzyme that breaks down penicillin and makes it resistant to the antibiotics. More likely, patients with cutaneous anthrax might get doxycycline, and patients with inhaled anthrax might get a combination of a bactericidal antibiotic, like ciprofloxacin, along with an antibiotic that inhibits protein synthesis, like linezolid. Now, as big of a deal as antibiotics were back then, a human vaccine would still be useful. And in the early 1950s, an Army research team came up with an anthrax vaccine based on the bacterium's protective antigen. Their vaccine effectively prevented anthrax in animals and was safe when injected into humans. But it was tricky to test its effectiveness, because purposely giving people anthrax is unethical. So, researchers decided to test it on folks who were already at high risk of contracting anthrax. People in wool mills. A research team led by Philip Brackman picked out 4 American mills in the Northeast. They averaged 1.2 cases of anthrax per 100 employees per year. They eliminated workers who'd already had the disease, then divided everyone else into 2 groups, one of which got vaccinated, one of which got placebos. At this point, they asked if people wanted to still participate, and roughly equal numbers in each group dropped out. Then they followed the mills over the course of 4 years. But the trial didn't go entirely to plan. One of the mills had a big outbreak of inhalational anthrax in the first year of the study, so they opted to vaccinate everyone who had only gotten placebos up to that point. Plus, since the trial was linked to employment, participants who left their job also dropped out of the trial, and when new employees started at the mills, they might not get the full schedule of vaccines. So ultimately, the researchers were left with 3 groups: fully vaccinated, partially vaccinated, or placebo. By the end of the trial, there were 26 anthrax cases among 1,249 employees. 21 cases were cutaneous, and 5 cases were inhalational. 9 of the 26 cases happened in that one outbreak in that first year. Only 3 of the 26 cases happened in participants who had received doses of the vaccine. 2 of those 3 had been partially vaccinated, and only 1 was fully vaccinated. Meanwhile, the other 23 of the 26 were either in the placebo group or participants who had refused to get shots. They had an epidemiologist at the CDC do the statistical analysis, and he concluded that the vaccine significantly prevented cutaneous anthrax infections. Brackman and the other authors finished the paper recommending that some at-risk groups get vaccinated, but this wasn't something that we had to roll out to the greater public. Over the next few decades, the FDA would go on to approve an improved anthrax vaccine called the anthrax vaccine adsorbed, brand named Biothrax. And it's still only recommended for people with a high risk of catching anthrax, like people who work in labs that study the bacillus or folks who work with livestock. Most people who do get vaccinated against anthrax get it before they're exposed, but as of 2015, the vaccine was approved for post-exposure too. Pre-exposure vaccination involves getting 5 shots over a year and a half, then a booster every year. Meanwhile, the post-exposure is 3 shots over 4 weeks along with antibiotics. It's a lot. Finally, in 2012, the FDA approved raxibacumab, the first monoclonal antibody for inhalational anthrax. And in 2016, they approved another, obiltoxaximab, although it hasn't actually been tested in cohorts of humans with anthrax. Both of them are highly specific antibodies that target and neutralize the bacilli's protective antigen. But unlike a vaccine, monoclonal antibodies are a tool meant to protect someone against an exposure, not a career full of exposure. And current research is looking at ways to target different antigens, like potentially the lethal factor toxin. But from what I've read, future treatments will probably be a combination of monoclonal antibodies and antibiotics. Now, if this were a normal infectious disease video, the story would probably end here. But you can't talk about anthrax without talking about biological warfare. Unfortunately, I'd get demonetized if I talked about it on YouTube, so I made a bonus video about that part of anthrax's history exclusively for my supporters on Patreon. I talk about some of the first uses of anthrax as a weapon in World War I, then the 2001 attacks, and the public health response to them. You can sign up here and get access to my ever-growing library of Patreon exclusives. Otherwise, consider checking out some of my other videos, like this one about the history of rabies. It's one of my favorites. Thanks for watching, y'all. Take care.